Alrighty then, how about some more practice within the topic of kinetics, chemical kinetics, the rate of a chemical reaction. How about some more practice with that method of initial rates? Hey, really, can you ever have too much practice? Maybe, but maybe you haven't had enough yet. Let's try some more. I know you'll see some on the exams. It's a very common way to see if you know about rates of a chemical reaction and to test your ability to think logically. So in any case, in the beginning, I have reactants A and B, and they're reacting to make C. I measure their initial concentration of A, the initial concentration of B, and see how fast the reaction goes. They're using the amount of C in molarity per second, the rate of formation, as a measure of how fast the reaction's going. But in any case, I decided to change this question, as you can see down here. Since we didn't hold B constant, I'm going to have a little bit of a tricky time figuring that out. And indeed, this video specifically wants to give a few examples of where I don't, as a stupid, careless researcher, where I wouldn't necessarily hold one of the concentrations constant. It could be that you don't have control over that. That's the only reason I can think of why you wouldn't hold one concentration constant and watch what happens to the other, because that really is one of the hallmarks of science, is to hold everything else the same and change one thing, watch how something else responds. In any case, if I hold in reactions, experiments 1 and 3, I hold A constant and B goes from point 1 to point 2. But wait a minute, what happens to the initial rate from experiment 1 and experiment 3 from point 1 in B to point 2 molar in B? And the answer is nothing happens. So if nothing happened to the reaction rate as a result of doubling B, then I must conclude that it's zero order with respect to B. Interesting. So I can more or less ignore B. So the amount of B doesn't matter in some way. Perhaps it's a catalyst. Perhaps some other weird scenario. It could be a surface thing. It doesn't matter how much B I have. So I guess I can ignore B. Point 1, point 3, point 2, point 15, point whatever. Doesn't matter. Yeah, hard to believe, but true. Looking at experiments 1 and 2 then, I see A goes from point 1 to point 2. That's a doubling in A. Does the rate of the reaction also double from 2 to 4? And the answer is yes. So therefore it's first order in A. So here's what I wrote. I said, this is all I just wrote down what I said earlier. In trials 1 and 3, A is held constant while B doubles, resulting in no change in the rate, so it's zero order in B. So I can basically ignore B in the rest of my thinking and logic and conclusion. And I already decided it was first order in A, because if I go from point 1 to point 2, that's doubling the concentration, I double the rate, so therefore it's to the first power. We might also ask, how do you find the rate constant? Did I ask that here? I should. If it's zero order in B, I might also just not bother to write it, and if it's first order, I don't often bother to write the 1, but when I'm first learning, it sure is handy to do that. Anything to the 0 power is 1, so put point 1 in here, it's just 1 anyway. But I could put point 1 here, and the rate in molarity per second here, and solve for K, a first order rate constant. Did I do that? Oh, here we go. Yeah. So the value for K would be 0.1 molar for A concentration, 0.0002 molarity per second for the formation of C, a measure of the reaction rate, and therefore solve for K, keeping careful track of the units. The molarity here cancels the molarity here, and I'm left with 1 over seconds or 1 over time for the units on the first order rate constant. Interesting. Okay, that's so much fun. Let's try that again. Might be handy to keep this out of scientific notation if at all possible. Sometimes it makes it more clear. Hey, look at experiments. Let's see, what are we going to look at? On this reactant C, they didn't hold it constant, 0.1, 0.2, 0.3, 0.4. They change it all the time. They're changing it up. Maybe I'll look at experiments 1 and 3. Yeah, that'll be good. In experiments 1 and 3, I hold A constant at point 2 and B constant at point 1, and I triple C from point 1 to point 3, resulting in the rate. What? The rate didn't change from 2 to 2 or 0.2 millimolar per second in each case. So if this one triples from 0.1 to 0.3, and that's subconstant and that's subconstant, and this doesn't change, I would say it's zero order with respect to C. So therefore, in my further reasoning, I can ignore whatever C does. Did I say that? I think I said that down here. So I'm going to ignore C in everything I do from here on out. But now I can go back and try to figure out the order with respect to B and the order with respect to A. In experiments 1 and 2, I hold A constant at 0.2 and 0.2, but I triple B from 0.1 to 0.3. If B triples from 0.1 to 0.3, does this also triple? 2 times 3 is 6, and this is to the same small power, and so yeah, looks like it does. So if this triples and this triples, I say it's first order in B. Let's look at experiments 2 and, well, yeah, right? You can do it this way. 2 and 4. In experiments 2 and 4, I'm ignoring C because we thought it was zero order, but I hold B constant at 0.3 molar and 0.3 molar, but the A is changed from 0.2 to 0.6. 0.2 to 0.6 is a tripling. Does this also triple from 0.0006 to 0.0018? And I think if I'm doing my mental math correctly, the answer is yes, it does triple. So if A triples and the rate triples, therefore it's first order in A as well. Did I write that? I think I wrote that. That's a lot of paper. Sorry about that. Yeah, there we go. So A tripled and the rate tripled, and there we go. First order in A, first order in B, zero order in C. Can I find the value of the rate constant? Keeping track of units? You should be able to, right? So I put from trial 1, or you could use trial 2 or 3 or whatever trial you want. The rate constant shouldn't change if the temperature doesn't change. And I use probably the experiment 1 molar concentration of B and of A to the first power to the first power. One of these m's cancels one of these m's, the other m comes to the denominator along with the seconds. And I have, yeah, you see the math? You know, you can't do this by osmosis. You'll have to practice some of this. The power of all this is that I have a rate law and a rate constant. I can determine the rate of the reaction without ever knowing or without ever trying it. But I could say what if I adjusted the molarity of A and the molarity of B? The molarity of C doesn't matter, but if I adjusted them, even in a theoretical sense, I know how fast the reaction would go, because I know the constant and the rate law. Let's try one more funky monkey one. Let's see, where am I at? I am, oh yeah, oh, I'm here, I'm here. Okay, cool. Last one, last example? Yeah, I'll give you one more after this, but I'll just leave it to you to look at. On this one, they're telling me it's first order in A and first order in B and second order overall. That makes sense. So I can write rate equals little k constant times A to the first times B to the first. But we have a couple of unknown concentrations, epsilon and beta, capital letters from Greek alphabet. I thought it would be nice to summarize. So keep this out of scientific notation, same for this. They told me it's first order in A and first order in B, so right away I go ahead and write that down. From this, I could, if I wanted to find the value of the rate constant, I could take 0.2 molar for A and 0.05 molar for B and 0.004 molarity per second for the rate and solve for little k. That's one way to do it. I think that's what I did here. And then I could say, all right, if that's my rate law and I've found k, then could I use this known and this known and this known and this known and this unknown as epsilon and simply solve for epsilon? And the answer is, yeah, of course you can. So if I knew the rate constant, 0.4, determined up here, and the molar concentration here, but didn't know this concentration, but knew the rate, all I do is just solve for that epsilon to the first power, and it comes out to 0.8 molar. Or you could use ratios. If I use ratios, it turns out you don't have to know the constant. So the constant stays the same, but if I compare this trial to this trial, the rate, of course, increases. The concentration of B stays the same, and I can guess what the concentration of A should do is to the first power. I solve for epsilon, things cancel out, and again it comes out to the same answer. But the point is my constants canceled, and I, in a sense, am mathematically allowed to do this um, to save brain power if you're tricky. Or the other way to do it, oh no, let's go ahead and figure out B. Let's use the method of ratios to, not B, beta. Let's figure out beta using let's compare, say, trial 1 to trial 3 and in a ratio. Did I do that? I think I did that. 1 to 3. Yeah, right, I did. Here's the ratio. And the units cancel and the constants cancel, and I have just a whole bunch of numbers in ratio, and B comes out to 0.2 molar. Or beta comes out to 0.2 molar. Interesting. I know I'm going quickly, but of course you have the pleasure of rewinding, pausing, asking, thinking, struggling. Here's one for you to try. Boy, if you were brave, you would you didn't see that, did you? You would pause the video right now and try to solve this. What's the rate law for this reaction based on the initial rates? 4 different trials. Find the value of the rate constant K. And yeah. Jeopardy music. You can pause it if you want, or since we were all lazy, you'll go ahead and keep watching and find the answer. Maybe I won't even show you the answer. Maybe I'll just post it on a PDF if I get to that point. That's a good idea. I'll torture you. Yeah, I'll see you in class, guys. Have a good one. Thanks for watching. Seriously. Thanks for working, studying hard.